Section 14.3 is the Pythagorean Theorem, the distance formula, and equation of a circle. So it's actually going to start with the Pythagorean Theorem, and that's the part we're going to take a look at today. The other two parts we'll take a look at on Friday. All right, so the Pythagorean Theorem says something akin to the following. If a right triangle has legs of lengths A and B, and a hypotenuse, which is the side opposite the 90-degree angle of length C, then A squared plus B squared equals C squared. And there are literally hundreds of proofs of this theorem. All right? One of them was actually written by a previous president of the United States, which is kind of cool. I don't usually think of our presidents as being mathematically minded, or at least not necessarily so. And he's credited at least with the proof of one of these, or with one of these proofs. Garfield, President Garfield, yeah. So, and I knew at one point which proof it was that he did. I've done a presentation on several of the different proofs of this before myself, and they're fun. Some of them talk about breaking things up in terms of pictures, so you can see like this middle picture right here. Well, let me talk about the first one. This is the picture with the A and the B and the C on it, and you can see somehow if you take these images and you piece them together in the right way, you get this box over here that's an A squared box and a box here that's a B squared box. And if you add the lengths here together, this is A plus B quantity squared. So there's some cool, fun algebra stuff going on here. Same kind of thing going on here. This length right here would be the C length. And so you're seeing this box in the middle is C squared, whereas the box over here's outer box is C squared, or is A plus B quantity squared. There's just some really interesting proofs that don't look maybe like the same one that you've seen or the pictures you've seen before of them. So just be aware of the fact that this is not one of those things where it's one way and only one way to prove the thing. There's lots of ways that people have developed to prove it. Our focus is going to be on using that information, of course, to solve triangles. And by solving, I mean finding the lengths of the sides. So we're going to do an example here. We're going to solve for x and for y. And what you want to see on this one is that there are several triangles present in this picture, right? There's a big outer triangle, and then there's two smaller triangles that are sort of embedded inside of the larger outer triangle. So what we're going to do is we're going to start with the big outer triangle because it's the most direct in terms of what you already have given in the picture. So if you think about the big outer triangle here, you've got your length x over here, and you've got your lengths over here. Which of those three values is the hypotenuse? The x. How do you know, Leah? It is. How do you know from this picture that it's the biggest side? It's opposite the right angle. That's one way to do it. I think that's probably the easiest way. You literally could take a ruler and see, like, oh, look, it's the longest one on a ruler. You might be able to look at it. Sometimes it's harder than others to look at that and actually make that call. But any one of those statements, the fact that it's opposite the 90-degree angle, by definition, is what actually makes it the hypotenuse. Okay? So it is, in fact, the hypotenuse. So when we're thinking about a squared plus b squared equals c squared, the x is the c. Does it matter which one's a and b? Not at all. Doesn't make any difference at all. So both of the other two side lengths, namely the 4 and the 4 radical 3, and I'm going to put 4 radical 3 in parentheses before I square it, those are going to be added together and they will equal the quantity x squared. This is a little bit more, I don't know, number computation than we normally do. You're welcome to use your calculator to do this, but I'm going to show you how to do it algebraically because it's not very difficult. 4 squared, you know that. That's 16. But when we've got the 4 square root of 3, that's the same thing as having 4 squared and square root of 3 squared. You know 4 squared is 16. What's the square root of 3 squared? 3. All right? So literally this is 16 plus 16 times 3. And it all equals x squared. All right, so what is 16 times 3? Grab your calculator if you don't want to do it in your head. 48, and then I need 48 plus the 16 that's in front of it. 64. All right, so how am I going to now find what x is? Square root. The square root of x squared will be x. And what is the square root of 64? That is 8. Okay? If there are components of that you just didn't like that I did it in my head, that's okay. You've got your calculator. It will do a fine job of working for you and getting those numbers. It's all right. But the answer is, in fact, 8. Now, if, in fact, we had units, we would put them on. But this one doesn't give me any units. It just uses the numerical values. So 8's our answer for x. Okay, everybody good so far? All right. The next part's more difficult, simply because if you take a look at this triangle, even filling in the 8 along the bottom, we don't actually have 2 side lengths of any of our triangles. So here's my 8. I'm going to do this. 8, there you can read it better. So if I decide that I'm going to look at y as though it's one of the legs of the left-hand triangle over here, I have the 4 square root of 3 as the hypotenuse, but I don't have either leg. I know the bottom part includes part of that number 8, but I don't really know how much of it. Do you see the problem? And the same thing happens if I look at this triangle over here. The right-hand triangle has a hypotenuse of 4. But again, I don't know how much the bottom leg's worth of the 8 that's there. It's a portion of it. It's smaller than 8, but by how much? So what I want you to do is I want you to think about some things that you have seen already this semester that relate these 2 triangles, little ones on the inside, to the outer one. And it doesn't necessarily matter which of the 2 small triangles we look at, but let's pick one so that we're all looking at the same one. You want to use the right one? Okay. I'm going to guess that Emily wants to use the right one because there's no radical. Yeah, that's probably what I do too, actually, so I get it. All right, so if we look at this triangle over here, we know we have a 90-degree angle. Agreed? Yes, the 90-degree angle is over here. So in terms of comparing this little triangle on the right with the big outside triangle, they are both right triangles. Yes? They are. Do they have any other angles that match up? They both have the 90-degree angles. Do they have another angle? The top one or the bottom one? The bottom one. So this is the one right here that they have that matches. In the big outside triangle, that's one of my 3 angles. And in the little right side triangle that's on the right-hand side of my page, it's one of my angles. Now, it's going to be easier for me, and maybe easier for you, if I draw the triangles separately, because when they're stuck together, it's harder for me to see what's going on. So here's my big outer triangle, and here's my tiny little triangle over here on the right. Is everybody good with that? I'm going to label letters. I'm going to call this A, B, C, and D. So here's A, B, C, and B, C, D. I'm going to put in my 90-degree angle markers, and I'm going to put in the angles that I just said matched, which are the angle C's. So far, all I've done is I've separated the triangles out and I've redrawn them, and I've marked the corresponding angles. What is the relationship between these 2 triangles? They're similar. Why are they similar, Lacey? Angle, yeah. These are similar by angle. So you guys did a test. Is it the test you still have, or was it the test from before? I think it's the test from before, right? That had similar in it, right? And one of the things I asked you on the test was about identifying which triangles were similar. And in identifying which triangles are similar, you actually had to write down like triangle ABC, similar symbol to the other triangle. We're going to do that next because that's going to help us make sure we get our sides in the right order. So the triangle ABC on the left is similar to what? So which angle is the 90-degree angle in the right side triangle? D. And in the left triangle, comparing the 2 here, it's angle B. So I know that D needs to be in the middle because the D has to match up with the B. Right? So this angle B matches this angle D because they're both right angles. So they're in the same location when I write them down in similarity arguments. And the angle C's are the exact same angle C. They're not even just like congruent values. They're exactly the same angle. So those are in the same location as well. So this C and this C are in the same spot because they're the same angle C, which only leaves me with angle B listed first. This is the similarity argument that I have. Now I'm going to put my side lengths in that I know. This is a 4. This is a 4 square root of 3. This is an 8. This is a 4. And what I really need is I really need to know what DC is on the bottom in order to find out what the DB is, or vice versa. I could find DB directly, and that would be okay too. That might actually be my best choice, is find DB directly. Let's do that. Okay, let's look at then what, this is the side I need. It's called Y, right? Which of the sides corresponds to side DB? Right. DB right here that I've just circled is in the same location as AB. And what is the angle, or what is the side length AB in the other triangle? All right, so I can set up a proportion. My proportion is to take that 4 square root of 3 and compare it to my side Y. That's what I'm looking for. The other proportion has to compare the other information that I actually know. The other information I actually know in my little triangle is this 4. 4 is side BC. So BC, whoops, is the ones on the outside, which corresponds to the AC that's on the outside. So notice I have this is my larger triangle, and this is my smaller triangle. Is everybody good with that? So I need the larger value on top. I need the side length AC to be on top. So what is my side length AC? It's 8. And what is my side length BC? It's 4. How am I going to find this quantity now? Cross multiply. Who's had proportional statistical reasoning? Does this look like stuff we did there before? It is. We actually talk about it in that class as well. So we're going to cross multiply here. So if I do 4 square root of 3, whoops, times 4, it will equal what? 8y. All right, so what's 4 times 4 square root of 3? Yes, you multiply the two that are outside the radical. The part that's under the radical stays the same. It equals 8y. And then what? Divide by 8. Our goal is to get y alone. So this is y on the right. What is 16 square root of 3 divided by 8? 2 square root of 3. So if you'll remember from algebra, pre-algebra, the simplification is with the 16 and the 8 here. They divide to 2 to 1. They both divide by 8. So you have 2 square root of 3 for y. This isn't a simple problem. I'm not arguing like, oh, look how easy that was. There's a lot going on in this problem. And it's very cumulative of the things we've done so far, right? I mean, you had to go back to chapter 12, right, in order to get the similarity stuff ironed out, even to start this problem. And if you don't have the right similarity argument set up to begin with, the likelihood that you stick things into a proportion in the right way is not real good. And if you decide you're just going to split the 8 on the bottom up into sort of, arbitrary values, that's really not going to work. You can't just decide, oh, it's 3 and 5 or whatever numbers you want. That's not going to work for you, okay? So there is, very little guesswork involved in this problem, but there's a lot that involves you going back and thinking through the details of what makes this problem tick. And if you had used the triangle ABD, the right triangle on the left, yeah, the right triangle on the left, it would have still worked. Your relationship would have been set up a little differently because you would have used the angle the angle A as the common angle that they shared, but you still would have set it all up in a very similar fashion. You still would have done the cross multiplying. All that would have been the same. Okay? All right. Let's see what I have next. It is also true that if triangle ABC is a triangle with sides of lengths A, B, and C, such that A squared plus B squared equals C squared, then triangle ABC is a right triangle with the right angle opposite side C. Okay, so fill in those details and let me tell you why this is actually put in here, because it kind of looks like I just said something that I already said. Right? Okay, so if you compare this statement to the one above on your page, the one over here, whoops, that was it, over here that says, if a right triangle has legs of length this, then this is true. What this is saying is, if you have a right triangle, the Pythagorean theorem will hold. That was the first statement. The second statement says, if the Pythagorean theorem holds, then you have a right triangle. And that doesn't always work in mathematics. It's not always a both direction kind of thing when you have an argument like this. Just doesn't always hold. So this is a unique fact about this particular equation. It holds in both directions. Right triangles are Pythagorean theorem. You have a Pythagorean theorem. If you have a Pythagorean theorem, you automatically have a right triangle. So those are equal statements to one another. That's what this is saying. All right, we have one other example with Pythagorean theorem. Does everybody have this piece written down and ready to look at that example? Okay. Can the numbers 10, 24, and 16 represent lengths of the sides of a right triangle? So how would you decide that with what you know about right triangles? Okay, so why the 10? What do you mean? Why did you select the 10 and the 16, Emily? Okay, so if this is a right triangle, then it's the two smaller sides that are together combined on one side of the equation, right? That's what Emily chose, and she's right. So this should be 10 squared plus 16 squared. And we don't know if it's equal, so I'm going to put a question mark. That's what we're trying to figure out. And then the third side, if again it's a hypotenuse, would be the 24 squared. So what is 10 squared? What is 16 squared? And what is 24 squared? 576. So what is 100 plus 276? 356. So what can you tell me about these two numbers? They are not equal. What does that tell you? Alyssa, what did you say?
It's not a right triangle.
This is not a right triangle because the Pythagorean theorem does not hold.